in science, where we'll be talking about, as it says on the tin, how we can use code in solving math and science problems. So we'd like to open with this very famous quote by Stephen Wolfram on computational X, which is basically when we transform a field that was previously done um, purely non-computationally to the computation that we can use things like Python and MATLAB and Octave and machine learning to address problems that we might otherwise address in a less nuanced way. So as Wilson puts, if one picks almost any field X from archaeology to zoology, then by now there either is or soon will be a field called computational X, and it's going to be the future of the field. Okay. So let's begin with the scientific method, something I'm sure most of you, if not all of you, are familiar with. First proposed
Whoa,
by
what's a scientific method?
that serves as the foundation for how we approach science. About all scientific research obeys the scientific method in some way, although it has seen a number of variants in recent years, and it features a few core components. So the first one is the research question. We need to discover a question that is of scientific interest and is falsifiable, so it can be figured out, proven or disproven through scientific evidence. So, of course, falsifiability is the gateway criterion that we often use before proceeding further with scientific research. So some questions are far easier to disprove or prove scientifically than others. For example, we might have a question like, actually, this is a good opportunity if anyone would like to think of falsifiable questions and maybe also some not so falsifiable ones. For example, is it possible to characterize does the fluid, the cerebrospinal fluid obey some type of mathematical fluid model that's actually related to some recent research in nature? Is Canada real? That's actually trickier. Does P equals NP? Does P equals NP actually brings us into mathematical surveyability, which is a topic we'll be talking about later. This might come across as I'm not sure how controversial, but a very not falsifiable question might be like, does God exist? Because currently, as we know, there is no, that's hard to address scientifically. I don't want to get into the mess that I don't want to get into a messy discussion about religion, and it was a statement about religion, but at least from a scientific perspective, currently there is no way to indicate if God exists or does not exist, and it is therefore not falsifiable by scientific standards. So you can prove it false, you can prove it true. Okay. Now the third part is the procedure that we use to determine if that falsifiable statement is true or false. Can we do it? Can we not? Does it act like we thought we would, we thought it would, the hypothesis, or does it not? And this leads into the results. So we collect and analyze the experimental results, and we compare it against the hypothesis. So is it true? Then maybe that strengthens some understanding that leads in the direction of our original hunch, our hypothesis, or does it not? And if it doesn't, then that's good too, if anything better, because it might open up some new scientific topic. So if you could move on to the next slide. So this approach to scientific discovery has been for most people costly and infeasible. Unlike in the turn of the 17th century when the method was first publicized, scientific history and knowledge was scarcely accessible for much of that time and known to few, and laboratories were growing increasingly costly. In 1965, Sibby Bedford, out of curiosity, I'd like to take a quick poll. Has anyone heard of Bedford? Her writing's wonderful. Wrote that many generations had passed since the laws of the universe were something a man might deal with pleasantly in a workshop set up behind his stables. So in the 18 and 19. Could you? I'm not sure who did that.
I've muted them. Sorry.
Okay, thank you. So indeed, in the 1800s and 1900s, science was becoming increasingly exclusive and elite. If you don't have the nobility to get into the scientific world, if you don't have the money to set up a laboratory, if you just aren't born in a place that's home to a lot of like scientific knowledge sources, then it's going to be pretty hard for you to get into science or even really realize that science exists. So, however, after the advent of modern computing, we can simulate the experimental portion in many instances of scientific research. Now, science is accessible to anyone with a computer. Computational modeling and computational problem solving have brought us significant recent advances in differential equations, epidemiology, stock analysis, biology, statistics, and more. Oh, that's a good question. Science originates from the Latin scire, to know, which became scientia, and then it went through some old French phonological transitions to become what we now call science. Okay, so the new approach to science also encourages a new mode of thinking that we call computational thinking. Word problems are an excellent way to test this new type of understanding. So let's start with something simple, the area of a rectangle. So let's analyze this statement and look at nouns and verbs. Calculate the area of a rectangle by multiplying the width and height. And multiply.
I suck dick, I'm gay, nigga.
Okay.
Sucking on your dad.
Okay, I have no... Good.
Balls like it's Baywatch.
I don't even know how to categorize this type of behavior.
It's fine. I've kicked him to the waiting room. We've not had this issue in any
I have
previous
no idea
workshop.
why that's happening here.
I'm so disappointed.
But please don't disrupt the discussion.
Bit me over on the big couch. Rip my pants down like a bitch.
Okay. Please don't do that. Like, it's also pretty easy to get caught, and that might hinder other aspects of the hackathon for you. Okay. So returning to the to word problems. So calculate the area of a rectangle by multiplying the width and a height. So in translating that into a computational program, we apply computational thinking, in that we can treat different parts of speech, verbs, and nouns as things as different types of keywords in a computer program. So we can start by doing what a linguist might do and just thinking about those parts of speech. Calculates a verb, area is a noun, rectangle is a noun, multiply is a verb, width is a noun, and height is a noun. So moving on, we can translate that into what we call a conceptual model, as shown by the flowchart here, where the nouns identify data values that will become variables when we put it in a program, and the verbs identify operations, how we proceed with the data values to manipulate them and get the things that we want to investigate in our scientific experiment. So we input width and height, and we insert them into the times operator, and that gives us our area. So then we can move from that conceptual model, and we get to what might be like more familiar computer science notation, in that we just multiply width and height, and we store it in an area variable. And in fact, you'd see this exact notation in a language known as R, if any of you are familiar with that. It's great for science. So next, a more complex example, something you might see in like a physics or chemistry course on thermodynamics. So here, because it's longer and it's kind of hard to get the arrow thing, italics denote verbs and underline denotes nouns. So calculate the energy needed to heat water from an initial temperature to a final temperature. The formula to compute the energy is the amount of water in kilograms times the difference of the final and initial temperatures in Celsius times 4,184. So we first translate that into our conceptual model. As again represented by the flowchart. We start with our initial and final temperatures, and we enter that into our chain of verbs, which are now operators. So we take the difference then we multiply it with the amount, and then we multiply it with 4,184, and we store that in the energy, which gives us the perfect answer. Well, perfect answer, right? The right answer, which again is in the more familiar computer science notation. We store amount times final temp minus initial temp times 4,184 in energy. So finally, let's think about the abundance of conditionals in problem solving, which involve previously described conditions. So italics denote verbs, underlined denote nouns, all caps denote conditionals, and underlined italics denote conditions. So here we have a slightly modified question. The area of a rectangle can be found by multiplying the length and width if both are greater than 0. So we can again translate that into our conceptual model. Next slide. Conceptual model, which again is the flowchart. So we have length is greater than 0, width is greater than 0. We enter those conditions into 8, which most of you probably know as a logic gate, and we have a conditional. If it's false, it's invalid. If it's true, it's okay, and we proceed with our usual way of calculating the area. Hello, Stiggy. So we might also encounter or type conditions, such that, for example, if distance is less than 100 or greater than 200, in which case we denote that in our conceptual model as inputting those conditions into the OR gate, which again, if it's false, returns invalid. If it's true, it returns okay. So sorry, since this is a big group, if some of you are having difficulty understanding something, it is kind of hard to address it, just each of you individually. But whenever you're confused, please enter that as a question in the chat, and I will try to answer it, given that they don't move too quickly. Okay, so now the last type of important logical structure we encounter in everyday word problems is repetition. And these all appear as loop structures in the programming languages we're so familiar with. In fact, you might see some of these exact keywords in like Python or Ruby. So first, we can recursive conceptual models will be addressed later. Okay, so first, 4. This specifies a range of values and the calculations to perform on each of the values in the range. For example, while the data values are positive, compute their sum. While this will specify a condition and the calculations to repeatedly perform as long as the condition is true. For example, until the data values are negative, compute their sum. Next two types, until, the opposite of while, will specify a condition and the calculations to repeatedly perform until the condition is true. For example, until the data values are negative, compute their sum. And lastly, all or every. This will typically specify a calculation to perform on all or every value. For example, compute the sum of all of the values less than 100. So all of those data structures that give us our conceptual model, that in turn give us our computational model, enable the construction again of a computational model. A model being a representation of a real system or a part of it. Perhaps you heard that word a lot if you attended the In Spirit AI workshop. So computational modeling makes models that require high performance resources far more accessible. So I have two examples here. First is the epidemiology, the study of disease model known as SEIR, which compartmentalizes disease into several stages and has a lot of complex moving parts to it. And really, we would be able to do a lot with SEIR if it weren't for like Python or C++. And next is statistical analysis, which especially for big data, which is probably a buzzword you've heard a lot, would be difficult to really execute or use computationally. And again, notice those flowcharts. The flowchart, again, is a very popular way of expressing conceptual models, the logical underpinnings of what we do. So next slide.
Just to add on a little bit, the SEIR model actually A lot of researchers have been using this to solve or to predict rises in the coronavirus,
Yes.
which is very relevant to today. In fact, I even made an API, I can send it later on, which it scrapes data off the New York Times website, which is daily updating cases per county. And what you can do is, based on this SIR model, which is available in packages such as in Python, you can basically predict how many cases will occur the next day. So this is a very relevant topic into what we're learning or what we are dealing with currently.
And another nice thing about the conceptual model that is the CO model, the compartmentalized model, which is very popular for modeling disease or similar phenomena, is that we can also easily hook it up or feed it into models that focus on some other phenomena. For example, I recently wrote a set of programs that get predictions from SEAL of COVID-19 to get a financial evaluation of changes in the agricultural sector. Okay, so let's recall what we learned about computational thinking to address the following framework for computational problem solving. So first, understanding and describing the problem in a clear and unambiguous form. Think about translating research problem statements into the flowcharts we've been discussing, for example. Number two, design a solution to the problem. This, of course, clearly is the most significant part and is what most of this discussion will center on. And three, developing a computer solution to the problem, going from a conceptual or mathematical model, as we'll later see, to a computational model, which often actually it can be the easiest part. Okay, so the development process, okay, here's a good question. I would prefer if people stop sending dumb questions in the chat. If I don't sound too abrasive, so it's easier to catch actually good questions like this. So does the SEAL model have relation to or not? Yes, it does. The or not is a parameter that the or not, which indicates how contagious and infectious disease is often a parameter, often a calculated parameter to many incarnations of the SEAL model. Okay, so the development process of the software in step 2 involves carrying out a sequence of activities, a process known as the software lifecycle. The simplest model of the software lifecycle is the waterfall model, and it's actually quite analogous to the development of a scientific model. So first, analysis, which results in documenting the problem description. No, actually, I generally don't encourage self-promotion during events like this in the Zoom chat, although what Schlock sent out is actually relevant to the discussion and what he just said, so I think it's justified. So analysis, first step, which results in documenting the problem description and what the problem solution is supposed to accomplish. Number 2, design, which involves describing and documenting the detailed structure and behavior of the system model. Number 3, implementation of the software using a programming language of your choice. For math and science, the 4 most popular languages are probably Python or MATLAB and Octave. Although there are also some newcomers like Wolfram, and there are even older languages like C++ and Lisp that are still used in some scientific research. 5, installation. 4, testing and verification of the programs, and number 5, installation, which results in delivery and installation of the programs. Finally, number 6, maintenance and continuing its usage, or developing upon it or making amendments to advance computational modeling and science as a whole. We'll be talking about that in quite some detail. So as per the name, it can be characterized in a waterfall flowchart. And if you ever go into software engineering or do a software engineering major, you will probably see these types of waterfall diagrams for software life cycles quite a lot. Spiral model. Actually, that is sometimes how the waterfall model is characterized. Anyway, so before we move on to the next part of this discussion, mathematical modeling. Oh, actually, on Octave. Octave is open source and it's free, and it has a lot of what MATLAB has. And again, they're both used for mathematical and scientific modeling. However, the main thing is that MATLAB has a lot of proprietary software that, while extremely impressive and often essential for mathematical or scientific modeling, is, again, proprietary, so they can price it however they want. And it's very expensive. Um, anyway,
Actually, I'd also like to add that Sage Math is really great too.
oh yeah, and Maple's pretty good too. And again, Wolfram's great, although it also costs money. Okay, so before we enter into the next part of our discussion on the mass of things and how we translate from conceptual model to a mathematical model to, finally, our goal, our computational model for testing, for engaging in scientific experimentation and evaluating hypotheses, let's discuss 3 quotes of caution. So first, a big computer, a complex algorithm, and a long time does not equate to science, very famously said by Robert Gentleman, in that iterative running of some complex algorithm, that's not necessarily science. Computational modeling is often applied to science, but it doesn't always have to be science. And there are also a lot of philosophical objections in doing so, often called the surveyability problem, which we'll be talking about. Number 2, statisticians, like artists, have the bad habit of falling in love with your models, said by George Box. So don't get it too attached to your model. Oftentimes the underlying assumptions are too bad or finicky, or you made some too big a leap in logic that ultimately causes everything to crumble to the ground. Don't cling on to it or anything. And oftentimes that leap in logic can cause such big changes that we really just have to start our logic over from the beginning. So don't get too attached. And number 3, the best thing about being a statistician is that you get to play in everyone's backyard. John Tukey. So statistics, which is closely related to just mathematical modeling in general, and such that almost no matter what the subject of your mathematical model is, you will probably have to employ statistical logic at some point, especially if your model is stochastic, as we'll be seeing. And that is part of what makes statistics such an exciting field, because you, as Tukey said, get to play in everyone's sandbox. So another big component of designing a preliminary solution is considering the math behind it. The need to evaluate complex equations or millions of operations is often why we turn to computational modeling in the first place. Modeling a situation mathematically allows us to reconsider the logic underpinnings of what we're doing, and we often consider 2 main types of models. First, deterministic models. Out of curiosity, how many people went to the causality workshop and heard Mr. Mueller talk a little bit about determinism? Yeah, good. So you're probably familiar with the fact that Spinoza was what popularized the notion of using determinism to think about math and science, as well as Laplace, who proposed the famous thought experiment Laplace's demon, wherein a demon corrects the probabilism of the world and can just use regular physics to characterize the entire evolution of the world deterministically, which, as per what it says on the tin, is kind of spooky to think about. Number 2, stochastic models, what I just said, which are far more chaotic and rely on probability and randomness. A different way of talking about deterministic and stochastic models is thinking about the conservation of information, in that for every instant of time, t, we have some value of the model, and we have an arrow pointing backwards so that we can follow to get some older value, or an arrow forwards that we can get some later value. So for determinism, that information, the presence of 2 arrows, is always conserved. we always know how to get forward and we always know how to get backward, at least according to the logic that the model uses and the assumptions it's constrained to. However, stochastic models kind of break that because we use probability to evolve from one state to the other. In contrast to running a deterministic model, the results we get from a stochastic model can be completely different every time. So let's start with the simpler, more classical way of thinking about mathematical and scientific modeling. And let's talk about the method of bisection. Could you go back one slide? Actually, a few more. Okay, yes. So let's take the bisection method, one of the first approximation methods. It's a very common numerical method. So it's a method that takes in numbers and iterates through them to find a numerical output that allows us to find the root of any continuous function for which we know two values with opposite signs. So first, let's examine the conceptual model and the logic, the underlying logic that we can use to approach this problem statement. So basically, we're going to need one core piece of information, and that is the theorem. Let f of x be continuous on the interval a, b inclusive, and let k be between f of a and f of b. Then there is a c between a and b such that f of c equals k. It's on the slide, but does anyone know what this is called? This very important fact.
I wonder.
It definitely doesn't say it on the slide to the bottom right or anything. Absolutely not. It's definitely not what it is. That's a completely unrelated image. Intersection method. Yes, it is indeed the intermediate value theorem.
IVT.
Also abbreviated as the IVT. And it might be one of the most important mathematical facts ever. And it's the underlying foundational fact of analysis, which is the mathematical study of change. And it sounds simple because really all it's saying is that if you have a continuous function, there are no breaks, so there are no breaks in it, and you know that there's one point below the x-axis and a point above the x-axis, then there has to be a point on the x-axis. Now that seems really obvious, and it is, but the IVT is nonetheless very important. The fact that we know that for a certainty, and one of the corollaries of that is that we get to use the bisection method. So like any mathematical model, the method of bisection has assumptions, which we'll talk about first. As previously stated, we must assume that the function being approximated is continuous. It doesn't have any abrupt changes in value, and our two input examples, f of a and f of b, so the function of interest evaluated at 2 points, x equals a and x equals b, differ in sign. So in a computational version of bisection, we can use conditionals to validate these facts, outputting something like can't handle this otherwise if the assumptions don't hold. And there's an entertaining XKCD for people that also love Randall Monroe. So bisection first evaluates the IVT on the course of the function. For example, let's take f of x equals x cubed minus x. So f of 1.5, which equals 1.5 cubed minus 1.5 equals 1.875, which is greater than 0, and f of -2 equals -6, which is less than 0. So f has at least one root over the interval, -2, 1.5 inclusive. And in fact, we know just from the fundamental theorem of algebra that f has 3 roots because there's an x cubed term. So we're good. Bisection then proceeds by halving the interval. The midpoint of bracket -2, 1.5 inclusive is -0.25. And since f -0.25 equals 0.2344, which is greater than 0, f has a root over the interval. Two observations at this point are: one, this new interval removes 2 of the 3 roots, and 2, we are guaranteed to be within 2 minus -1.5 over 2 equals 3.5 over 2 of a solution to f of x equals 0. So this algorithm then continues by halving the new interval and removing the half that no longer guarantees a root. Bisection is often called a Bracketine method. Um, so we just have to take in 2 points, one that's greater than 0 and one that's less than 0, to iterate through the intermediate value theorem. So continuing for several iterations gives a fairly close answer as we approach one of the roots, x equals -1. So you can take a look at the table. So for the 0th iteration, we have the original value. For the next one, we go between, we have them, we bracket them, and then we keep doing that again and again and again until we look at the 5th iteration, which centers around -1. And as we keep going and going and going, it will converge to a interval that just contains -1. You can also see this graphically. So mathematical modeling also allows us to perform the error analysis of other models. So modeling the properties and behavior of other models, like where things went wrong, is known as meta modeling. And so we could determine exactly how accurate bisection is. So the algorithm's estimate of the root for the previous example for the 5th iteration is 1.5 plus 2 over 2 to the 5th, which equals 0.1094. Yeah, some of the more interesting numerical methods, like the Runge-Kutta method or Newton-Raphson, or Born-Infeld, do involve more complex math, which I would love to get into, but I don't think everyone here knows differential calculus. So anyway, so since we're basically just going in half and we're multiplying that k times for k iterations, could you go to the previous slide? Thank you. And so the algorithm is going to be within 1.5 plus 2 over 2 to the k. Oh no, you don't, I'm not, if you're being sincere, don't feel dumb. This is very specific. I don't think any high school regularly teaches the bisection method or the history and logic of mathematical modeling or meta modeling in its curriculum. And in fact, the main point is that I'm teaching something that most high schools don't teach, but is nonetheless very important for math, science, and programming. Anyway, so for example, let's say we want to be within 10 to the -8 of a solution, i.e. we want to be accurate to 8 digits. So let's find the first integer value of k such that 3.5 over 2, again 1.5 plus 2 over 2 to the k, is less than or equal 10 to the -8. So we just take the formula for the error, which is an exponent with the number of iterations. And we just set that equal to 10 to the -8th. And we get the integer value, which is going to be the rounded up value, rounded up solution to that equation, which is the natural log of 3.5 times 10 to the 8th over the natural log of 2, which equals 29 iterations. I wanted to talk about the bisection method because it doesn't involve anything at least superficially complex like integrals or derivatives. But I will be sending the slides out after. I will be sending these slides out after in the Discord so you can review it. And also don't hesitate to ask me, Schlag, or any of the other organizers questions about the material in Discord. So bisection does have its limitations. It is now considered a fairly crude root finding method, having a fairly slow convergence rate. So for example, in the past example, we got to -1, and we got to something that's fairly close to -1 in the 5th iteration, but it would take many more to be absolutely certain. And frankly, x cubed minus x is kind of a particularly simple example. So it could take hundreds of iterations to like be certain of, to get a close approximation for some of those functions. And it also requires fairly specific conditions to be used properly. So let's make small amendments to the way we characterize things and how we advance. So making small amendments to the way we characterize things is how we advance mathematical modeling. And it is often the smaller aspects of a system that are the most complicated. So I attached an XKCD comic. So it's about a physicist it's about a new physicist who's talking to an older physicist who's complaining about how modeling is easy because he's saying that we can predict the behavior of a complicated system by modeling it as a simple object and then just adding secondary terms to account for complications he just thought of. Which frankly is what most scientific criticism boils down to. And it is misguided because again, it really is often the most complicated aspects of the system that are the smallest. So we can usually at least get a good approximation of how things behave by just modeling it as a simple object. But it is very rarely just as simple as adding secondary terms. Okay, and also here's one last bonus in that in translating the mathematical model of the bisection method to a full computational one presented in generic pseudocode. So the hat signs over here, if you've never seen that before, that just means the observed value. So basically all this is saying is that it sets k equals 1. So while the termination criteria is unmet, i.e. The condition that makes it keep running is satisfied, then we do some things. So we set the observed value of x hat, to a plus b over 2. So remember how we did 1 plus remember how we did 3.5 over 2 before. And if the sign of the function equals the sign of the function at the first value, then we set x hat to that value. If the sign at the value of x equals the sign of fb, then we set x hat to b. And otherwise, if there is no sign and f of a plus b over 2 equals 0, then we set the termination status to true because we found a root. And in fact, we found a very accurate one because we know that it's going to be the exact same answer if we're literally just given points that are halfway to the root. And so we just continue that over and over and over again, increasing k each time. And the function will then stop as soon as the computer and the approximation gets so precise that the computer can't even distinguish between the precision of the approximation and the actual answer. Which takes a really long time. So especially if you're using a programming language that's especially nitpicky about precision, then you're really going to feel how slow the convergence rate for the method of bisection is. And it might take like 10 minutes to get a result or something. Okay, so let's talk about stochastic modeling. Yeah, basically, epsilon being a tiny value. So long as the epsilon is so tiny that the computer or the programming language used isn't even precise enough to recognize it, yeah, then the termination criteria is met, and we have a good approximation from the bisection method. So a very common class of stochastic models is known as the Monte Carlo methods, and they had a large part in liberating calculators, humans ordered to do menial calculations, often scientists' wives. It was a fairly misogynistic culture back then, from their incredibly tedious jobs and bringing computational science into view. So Monte Carlo methods rely on repeated random sampling to obtain numerical results with an underlying conceptual model that uses randomness to solve problems that might be deterministic in principle. So one popular example of that is how telecoms use Monte Carlo methods to assess the network performance in different scenarios, helping them to optimize the network. So that might seem like a deterministic problem in principle, but really, if we rely on randomness and repeated and random sampling, then that's really going to be the gateway. Monte Carlo used in the Drake equation. You might be thinking, yeah, it is actually. You could call it the Drake equation. The Drake equation does kind of fall under Monte Carlo methods in that it's basically just multiplying sample sizes that are increasingly tiny. Okay, so moving on. So in their most general form, Monte Carlo simulations take the most uncertain variables and takes the most uncertain variable in a problem and assigns it some random value. The model is then Yeah, the Drake equation is famously simple, but to be fair, Drake literally wrote the Drake equation on a cocktail napkin. Just to be originally, when asked about it at a cosmology conference or something. And it was mostly just to be an example of how we can address a cosmological value like the number of extraterrestrial organizations that we can communicate with by multiplying increasingly short probabilities. So now the Drake equation probably isn't right, but the underlying conceptual model of it likely is. So it's a pretty fun lesson in computational modeling. Thank you for, well, in like scientific modeling. Thank you for bringing it up. So the model runs by assigning it some random value, and it eventually provides a result. And like the bisection method, this is iterated again and again and again while assigning the variable in question with many different values. Once the simulation is complete, the results are averaged together to provide a resultant estimate. So I have another great XACD comic here. So it talks about ensemble models, which is basically where we combine different modeling techniques. So for example, the model in Shor's algorithm, which is a quantum algorithm used for the factorization of large integers, combines both deterministic models and stochastic models to get a really big model that frankly is that's really impressive and is the pinnacle of quantum computing, although we don't have time to talk about that. So um, as Monroe puts, forecasters run many different versions of a weather model with slightly different initial conditions, and this helps account for uncertainty and shows forecasters in a spread of possible outcomes. So then some of these outcomes might include universes where rain is 0.5% more likely in specific areas, wind speeds are slightly lower, pressure levels are randomly tweaked, dogs run slightly faster, there's one extra cloud in the Bahamas, Germany won World War II, snakes are wide instead of long, Will Smith took the lead in The Matrix instead of Wild Wild West, swimming pools are carbonated and sliced bread after being banned in January 1943 has never re-legalized. So I also have a link here. Thank you for typing it out, John. That shows some really incredible software on GitHub for running Monte Carlo simulations. So if you're thinking of doing some type of stochastic modeling for your AngelHacks project, or you're doing it already, then if you haven't, I really do recommend you check out some of the incredible projects there. Okay, so why don't we move on? So finally, let's think about some of the philosophical objections to what we've just talked about. So the relationship between mathematical modeling and computational problem solving spurs concerns among many, as Thomas Chomsky most famously articulated. In doing that, are we just replacing logical deduction from assumed axioms with trust in an empirical computational process? So mathematicians seeking computer-assisted proofs are subject to any errors or accidents in the programs written, as well as defects in the runtime environment in hardware. Now, personally, I think that Tomosco is just being a little edgy in proposing this, although it does raise some interesting questions in how unsurveyable, non-surveyable many computational models are. A word we'll be talking about more in just a second. But first, I'd like to bring your attention to another amazing XKCD comic. In that people who think that the encryption methods on their laptop are incredible, realistically, if someone wants to break into your computer, they're probably going to, I don't even know if I should say this out loud, but they're not necessarily going to listen to how incredible your 40% bit RSAs are. And so solving computational proofs is seldom that easy. Please do not drug and hit people with $5 wrenches to get access to their private information. That is just a disclaimer from AngelHacks. So the characteristic of computational models and solutions is known as non-surveyability, as I've said multiple times by this point. However, in the case of scientific models, properly surveying a computational model can just be a matter of getting the right resources or reducing the problem to a simple one that's often called reducing the quadrature. that can be confirmed in the lab or on the field. For pure math, though, as Tony Oy and Ludwig Wittgenstein have discussed, except for trivial cases, contemporary software is modularly encoded and is required to satisfy a large set of specifications and is developed so as to interact with other programs, systems, and users. A full survey of a computational solution can really be close to unachievable. Luckily, science doesn't really suffer from that problem, at least not quite as much. Because science is bringing back full circle kind of to our original discussion about falsifiability. Science is a lot more falsifiable than math because whereas math is extremely abstract and there's often no way to really experimentally confirm if a solution or proof works or not, other than just thinking about the logic really hard. In science, we can just run the experiments ourselves and see what we get and see if that supports it or not, supports our hypotheses or not, or the computational model or not. So here is a summary flowchart. Yeah, okay, higher dimensional geometry and differential geometry, sure, but honestly, that's mostly just because that ties into physics. That's just that's just math that piggybacks off of physics. Okay, I mean, I guess you could say it the other way around, in that general relativity is largely physics that piggybacks off of math, but still, I'm going to say that because it's more convenient for the subject of this presentation. Could you go back one slide, Slock? So one last thing is going to be this summary flowchart for what modeling is in total. So we first have a real world problem, and we can address that more abstractly, mathematically, through specification, abstraction, and decomposition. So specifying exactly what the problem is, i.e., for example, like selecting parts of speech and thinking about conceptual models through flowcharts, as we did at the beginning of the presentation, on decoupling it into subproblems. For example, if there are conditionals, the first part of the problem might be validating or testing those conditionals. Next, we have our conceptual model, which is kind of exactly like this flowchart. So we think about the logical steps the deduction needed to get our desired result. And then that leads us into our next step, converting each part of the flowchart or conceptual model into a mathematical one. So then with that mathematical model, do we make the tricky leap to computer science with aided by CS concepts, principles, and methods, many of which were discussed here, we finally move into our computational model. And with our predictions and interpretations, we can validate it with science, for example, should we have the technology to. The two most common reasons for resorting, or well, not necessarily resorting, but hinging. For hinging on computational applications in approaching a problem computationally with computational thinking and computational modeling and computational systems is generally because we don't have the technology to actually do it in a traditional scientific approach. For example, we want to we want to analyze or test the possible behavior of a composition of some material by testing out different possible compositions and seeing which one exhibits a predicted behavior closest to the ones we actually do observe, and when we don't have like mass spectrometers advanced enough to decompose it. Informatics fit into this flowchart. Well, really, you need informatics just about at any stage in the process. Data will continually inform decision-making in scientific and mathematical modeling, but I'd say that informatics most comfortably fits at around in between specification, abstraction, decomposition, and the conceptual model. That's at least what an actuary would tell you. Okay, with that, thank you very much for coming. Does anyone have any last questions? Oh, and also,
Before we get to the questions, I had something that I just wanted to show. had to do with how many of you, I just have a quick question for you guys. How many of you guys have studied biology or interested in like cell biology, anything that has to do, it's related to the scientific method. And I just want to run through a quick example of how you would do that. So can we just see it in the chat to see how many people have done biology or like biology? Okay, that's awesome. It seems like a lot of you guys. And I have a quick example that I do want to show you. So this is just a random data set that I got from like a lab. And it's the example that I'm going to go through is, this is just basically the data I get. I have a specific gene ID, spot ID, time, spot, and the spot fluorescence. So essentially what happens in a cell is it basically splits into two, and that process is called mitosis. And what happens is that these when a gene is split, using specific research mechanisms, people are able to identify how much of that split's happening, which is basically what a spot